This is page 11 of the fault tolerance notes, and section 4 is about the Byzantine generals problem, or BGP. And the text reference for this is section 13.5. So back when we were talking about the distributed clock synchronization, I mentioned about a clock presenting different values to other clocks in the system. So that was an example of a Byzantine failure or Byzantine fault. So a Byzantine fault is the arbitrary failure of a component, and the way it behaves is that it can present different systems to different observers, or another way of saying it is that it can communicate different values to different components in the system. So it may present, I'm going to try and squeeze this on one line. It may present different symptoms to different observers. And another way of saying that is that it may communicate different values to different components. And what you want in a Byzantine fault-tolerant system is for the non-faulty components to behave correctly in the presence of a Byzantine fault. So I'm going to talk about Byzantine agreement, which is how you arrive at Byzantine fault tolerance. So with Byzantine agreement, all non-faulty components reach the same valid conclusion. So they might be agreeing on a value that's read from a sensor, or they might all be agreeing on an action that should be taken. As two examples, the two main examples. And Byzantine agreement is a tough problem when you have things failing in arbitrary ways. What the Byzantine generals problem does is it simplifies the problem a bit, and it says, let's say we're talking about a value that's been received. Each component in the system is going to act as a Byzantine general and tell the other components what value it received, and they will check with each other to see if they agree with what they heard from that one component. So each component will have a reliable way of knowing what each of the other components said. It might be easier to explain with a paper here. This image is in a paper called From Byzantine Consensus to Byzantine Fault-Tolerant State Replication Machine, blah blah blah, and I just want to focus on the Byzantine generals problem. So this is, in this example, we have 4 processors in a distributed system, and they're receiving an input. So if this was banking, it could be a customer saying to move some money out of the account or something like that, or in a rocket it could be reading the value of a sensor. And in any case, they've received this value, and now they want to know if they've all received the same value. And so what they will do is they will each initiate the Byzantine general's problem. So first P0 will be the general. It's going to broadcast to the other three processors what it heard, and then they're going to talk amongst each other and see if they agree with what they heard from P0. And then P1 will broadcast what it heard to the other three generals, or the other three processors. They will talk amongst themselves to make sure they think what they heard from P1 is the same, and so on. So now each of them will know what they believe that each of them says they heard, and so then they can reach they've reached consensus on what they heard from the client or the sensor. That's the reliable broadcast box here. So that's one Byzantine general's application, or Byzantine consensus. And then the second box here basically repeats that, where they're each saying, here's the action I think that should be taken, and they reach consensus on what each other said, and then they'll send the value back to the client. So that's the application, but we're going to be focusing on just this one step where the general is broadcasting a message to the other generals, or the processor to the other processors, and then they're going to talk amongst P1, P2, and P3 will talk amongst each other to make sure that they agree on what they heard from P0. That's the Byzantine general's problem. So let's go back. Okay. So the Byzantine general's problem was described in a paper by our old friend Leslie Lamport, who won the Turing Award in 2013, and the website, the Turing Award website that describes his contributions, is a pretty interesting read. Lamport was working with Shostak and Peace at the Stanford Research Institute. They were working on a problem for NASA, and it was I believe in rockets, and the control for these rockets, and they had to have high reliability. So Lamport liked to describe things in terms of analogies, and so this is one of those analogies. So the components are represented as generals, and faulty components are represented as treacherous generals, or we'll just say traitors. And the idea was that you would have the Byzantine army had surrounded a city, and they were deciding whether they had the strength to attack and win, or if they should retreat. And so you had a number of generals in charge of their troops, and they needed to reach an agreement. So in this case, they are going to observe the enemy, and they need to come to their common decision. That would be the Byzantine agreement. But it gets simplified to one general telling the others what the command should be, or attack or retreat, and then the others agreeing on what they heard there. So the commanding general sends a message, and to keep things simple, it is attack or retreat to n-1, where n is the total number of generals or total number of components, to n-1. Now, when you look at that, at least when I look at that, I want to say lieutenant, but in Canada, as in I think Great Britain, Australia, it's lieutenant. I don't know why. Anyway, lieutenant generals. So we'll see if I can get through the rest of this part of the notes saying that, pronouncing that correctly. So all of these generals, the commander and the lieutenant generals, communicate via oral messages. So they have messengers on horseback that ride back and forth between generals with their messages. So the first point about the communication is that it is pairwise. So it's not like one general shouts and they all hear them. The general will send a messenger to each of the other generals and so on. One of the assumptions is that every message is delivered correctly. It's a simplifying assumption, so it's not going to get garbled or corrupted on the way. Another assumption, and this is important to the algorithm, is that the receiver knows who the message is coming from, so knows who sent it. And finally, the absence of a message is detectable. So one way for things to fail is for a message not to get through. And if that happens, it will know, say after a timeout period, and it will just assume a default value. And so the default value, so the default is retreat. So this will be used when message is not delivered, or when they're deliberating and there is a tie. So if there is a tie decision. For half of them to attack and half to retreat would be disastrous. If they're going to attack, they need to attack with all their numbers. Okay, so the solution to the Byzantine generals problem is called the OM, or oral message algorithm. And this requires, as in the distributed clocks, it requires 3m plus 1 generals, where m equals the number of traders. So here is the algorithm description. So we have OM for 0 traders, and the steps are simply the commander sends value V to every lieutenant, and then step 2 is each lieutenant uses the received value as its decision, or retreat if not received. So that's pretty straightforward, but it gets more complicated. So now we have where m is the number of traders and m is greater than 0. So for step 1, it is actually the same as above. The commander sends value V to every lieutenant. Step 2, each, I think I just said lieutenant, each lieutenant acts as commander in algorithm OM-M-1, sending V to the other n-2 lieutenants. So a general does not send a value back to another general from whom it's already come. So that's why it's n-2. And so that's why it's important that it knows who the message has come from. That information is going to become part of the message, as we'll see. Okay, and finally, step 3, using the values received in step 2, Lieutenant I uses majority of the values that are heard, V1, V2, including its own value, as its decision. So let's see on the next pages how this works with first one trader and then two traders.